Our next speaker is Yuh-Renn.
Okay. Okay, so today I'm going to talk more detail about the programming, the 3D random alloy simulation. So we perform the coding and the implementation. So I'll take some details, and I know some part of the detail is very, disputed, but if you feel free to ask any question. I almost know all the coding details, so because almost means okay. Okay, I code all the code, so except that they do the machine, the student do the machine job. So you can ask me for any detail how the code was written, okay? So let me introduce that. So let me introduce that I'm personally interested in the device modeling. So I'm working on developing a real simulation tool that can handle all the problem of LED, but not just limited on LED. I actually interested on transistor or other device. But I just let you know that this is a typical LED structure, and you need to consider many things like contact resistance, current spreading. A couple of just say that you have a 2D, 3D, so you have current spreading, you have defect, you have alloy fluctuation, you have dislocation, and even in micro LED, you have the sidewall surface recombination issues. So that will affect your efficiency. So you have many things to consider. You need to consider carrier transport. You need to consider how to design quantum well to give you a right emission wavelength. And you want to lower down the voltage, so you need to compromise from composition, quantum well number. And you need to consider about the defect, dislocation. And you even need to think about the leakage related to this defect or dislocation, and electron blocking layer, current spreading layer, and finally something that is not related to electric problem, light extraction. So you have many things to consider, and also thermal management. So it's very hard to do a multi-scale modeling. If you want to do very detailed, then you put the whole region. I just tell you that you will do it forever. You will never get solution. If you do a very, very tiny and but also include very large domain, so your mesh size will be very, very large. Just how large? Probably the memory you need is 100 terabytes. Okay, so it's very hard to do that. Okay, so sometimes we need to separate the problem into different pieces. But I think that in the afternoon, a couple of already introduced that this is a typical gain nitride LED. So if you just consider about the carrier injection, it just shows that because this piezo barrier, so it's very hard for carrier to inject into the quantum well. Okay, so if you consider about the tunneling effects, if you simply consider the quantum effect, you may have some tunneling in this triangular barrier, but your voltage is still limited. And if you go to green, even you consider quantum potential, it's useless, honestly speaking, that because your potential bending could be too EV if you consider the real polarization. So some simulator will use smaller polarization, but we don't consider about that because if you use smaller polarization, your quantum confined star phase is also wrong, and your emission is also wrong. So it's a problem of that. So this is real experimental data, and this is the simulator give you what simulator give you. So there are two things. First is that we need to include a quantum effect, okay? And the idea of including the quantum effect that Marcel just introduced, and also a couple of also introduced, there are several ways to implement this. And the second is that we are considered about the alloy fluctuation. Because alloy fluctuation, what we found is that it will affect the recombination zone in the space. Also, it will also affect the potential barrier in the spatial domain. So if you, okay, no power, oh, sorry. All right, so, okay. So if you consider about the LOE fluctuation, and then we found it will affect the IV curve we are fitting. And we published a paper like, I think 2012. Okay, let me take it. This one is better? Okay. And we found that a lot of time we don't consider about the quantum effect, but we simply consider about the LOE fluctuation. If we don't consider the quantum effect, we already find that it reduces the simulation voltage a lot. It's almost close to the experimental effect. But at that time, the quantum effect is not included. So it's a little bit larger, but I mean, there's something that we can try to do more. Okay, so let me explain why. Sorry. Okay, so if you want to do the whole simulation, we have a lot of issues that, for example, if you want to consider the atom size random LOE fluctuation, that the best model, I can believe that Stephen tomorrow he will introduce that using tie binding, you put random LOE, and you can more accurate to know the real emission. But if you use tie binding, use random LOE atoms, you still limit in the space. I mean, all the space is decided by the number of atom size. So you cannot do it to do the carrier transport. If you want to include the Poisson carrier transport, you got some problems. I mean, nothing is perfect. We need to make choice between different methods. Okay, so I cannot say our method is the best. I mean, just in the interesting domain I want to study is that I choose this method that could give me some better simulation result. Okay, so something we need to fight. But the typical problem for the grid diffusion issue is that if you think about a diffusion model, okay, diffusion model is the divergence of carrier density, okay? So if you're using the diffusion model, it just tells you that your carrier distribution needs to be flat. Because if your carrier distribution is not flat for this flat quantum well, then the diffusion term will, because there's no electric field. So during diffusion part, if there is no electric field, if your carrier density is like a wave, it's not allowed in the diffusion solver. Diffusion solver tells you that, sorry, your carrier need to diffuse out and your band need to be flat. So in a quantum well, you will never get, in a common quantum well, you will never get a wave-like carrier distribution. I mean, that's because it's limited by the equation itself. So, okay, so then how to model this is that I think, okay, next page. I think there is some way introduced is the effective quantum potential. So a couple of just introduced that there is a quantum effective quantum potential. The idea is that this is the real EC in the quantum well, but actually consider about a quantum confined effect and the sum of the penetration in the barrier. So the real effective quantum barrier seen by the carrier is not the square, it's something like this, okay? And how to calculate, you need to do some convolution of your carrier density distribution, and then you come back to calculate effective quantum potential. So you still need time, especially the method it provides you need to solve the eigenvalue, eigenfunction, and it's okay for 1D simulation. But just like what I said, in going to 2D, 3D, the time consuming to get effective quantum potential is almost impossible. But if you really include effective quantum potential, you will find something interesting is that the internal there is an electric field coming in. So in the flat band quantum well condition, you think that you will never get carrier density to be like wave-like. But right now, the potential is not square. It's like this. So the electric field inside, the internal electric field inside is not zero. So it will compensate with the diffusion term. So the diffusion term force it to flowing out will be canceled by the electric field comes in. So with this picture that it's really possible for us to enable the diffusion term in the simulation. So that's a very key point. If you just simply put some wave in this equation, it's not working. Because if you want to consider tree diffusion, then diffusion term already tell you cannot do this because it's limited. The other trick way is that, okay, I don't want to simulate this domain. I put this domain is a break bus. So I say this domain is like a wave. Then all carrier flows in. It's just like a frozen carrier. And then that's another way. There's some software using this kind of approach. But when I was here, I remember that time, Marcel, they came to give a talk, okay? Then I feel that they say, okay, this is a landscape model. And at that time, they don't say it's like affected quantum potential. I think it's proved later, is that right? So, but at that time, I feel like this kind of wave is very like the real quantum system that we can model. So I just asked them if they can prove something like affected quantum potential, then maybe we can simply put this into the code, because it might be very hard for some people to implement this into a code, but since we develop all the coding, so I feel it might be, actually we finish this code just in 1 week. Just tell you the truth. Okay, so because we already have everything ready. We have the Hamiltonian of Schrödinger solver, so we just change this to eigenvalue problem to the boundary value problem. So we did it very quickly. And then laterally, Marcel just proved that it's a very good approximation in the carrier density. Okay. So I found that it's not just limited in the randomized potential. Actually, recently we used this tool to study the type 2 superlattice. Okay, this is the type 2 that this is a quantum world like type 2 superlattice. So in the traditional way, want to model the type 2 superlattice, they want to calculate the eigenvalue of this band and the eigenvalue of this band. Then how they model this model is that they look at it's a tunneling superlattice. So they cut this potential. Manually they cut this potential and create a new material effective like a smaller band gap. And then they do the simulation. So we found that if we get the effective quantum potential, this is the effective quantum potential, U of EC, then we don't need to do this. We can directly apply this in the tree diffusion term, and then we can directly simulate the infrared flow detector. And somehow it's good that we try to fit the responsivity for the experimental partner, what they do, and we apply this model. We don't get too much problem to get very close fitting, and we are not blocked by this barrier. So I just want to mention that this model is not just useful for the LED randomized problem. It can be applied in many device applications, except that there's a, I think you mentioned that the potential problem, reference potential problem in the high energy part. So that's the only issue that we need to solve. So this is like a type 2 superlattice. So actual real simulation domain is carrier flowing through this superlattice. And you can see this is effective quantum potential, and this is original EC. If we turn off the landscape model, we cannot get any current because this is just like a it's like a real barrier, so it's not tunneling. Okay. All right, so the target is that try to coding these three together and how to solve it. So just let me go very detailed of how we did that. So Marcel already introduced this, but I will give some more detail. So the first step we need to do is that we need to generate a composition map. So the way that we generate a composition map is that initially we seed a random number of Indian and atom number depending on the composition we are interested in. And we use random number to generate. So the generate side is using the lattice size, so the average lattice size in the grid. So we get the, I think lattice size we choose is 2.833 angstrom for gallium nitride. Then we found that this is a, if we don't take average, that our composition of course is like a digital quantum well, either 1 or 0. So if you decide either 1 or 0, I think Jim suggests that if even you took 1 or 0, you can get the potential after calculating the effective quantum potential. You should be right. But the problem is that if you only have one atom, then the one atom's band gap, I mean, just single indium nitride, one atom is not crystal. So its band gap, you cannot use 0.7 band gap. Effectively, you need to reconsider something that I think that the Taiwan model may give you more description. So if you want to use effective mass theory, we still need to take some range of averaging effect, like Gaussian averaging effect, to give us a reasonable indium composition. So it's very arguable that why we choose sigma equal to 2a. Actually, we try 1a, 1.5a to 2.53. And if we go into 3 or 4, then it's just like flat, totally averaging out. So you just see 20%. And if we go into 1, it's really like digital. But I think the problem is not digital. The problem is that later we will discuss how to calculate the strain and the polarization. So the problem is in the strain and the polarization part. If we just think this is a single indium nitride, the polarization is the strain. The strain is really, really high. So locally it induced too large polarization, and then you can find a potential barrier, even consider fluctuation, is like a huge barrier. So it makes some problem. So that's the reason. Then, but if you use digital, that you see a stronger tail. Also in the absorption spectrum, the tail, Marcel just showed, the tail is the sigma is the diffusion, the decay constant is much larger. Also, it's not good fitting. So we try, and we think that since like a quantum dot system, typical quantum dot system is like a few 1 or 2 nanometer, you can form a quantum dot. So it's effective math theory that using this kind of, we can use effective theory to calculate quantum dot size reasonably with this kind of size. So we roughly choose 2A to give a better fit. It's an open question that which one is good, but I think maybe in the near future we're working on Taiwanese model, or maybe Stephen can give me answer what's the better choice of that one. But after we got the composition, after chosen, we have a finite matter H. Finite matter mesh may not be the same size as the crystal structure. So even in some position in the z direction, the mesh size is even smaller than the atom distance. But in some lateral direction, because there is no heterojunction. Okay, so we put the larger, because it's a compromise between the speed and the efficiency. Okay, so we put a little bit larger. So the position of your atom composition to the finite mesh is different. So we need to do some linear interpolation to get effectively composition in this region. But this is a linear interpolation, so it will not change too much of the original indium atom composition. Then the second step is that we need to calculate the strain. So if we use the valence force field model for atomic size, we probably don't have problem if we just choose single indium nitride gallium nitride atom. But the method, because of the domain we want to calculate is quite large, so we decide to use finite element-based strain stress solver. So the basic idea is that each mesh element, you have the different volume, and you have suffer different stress and the external force. But actually, external force is 0. So you can solve this strain stress with the tensor. This tensor is decided by the indium composition. That's what I say. If you put the digital indium, then you get very large lattice size of the indium atom. So you get extremely large extremely large the strain locally. So you get very strong stress. So that's a problem. Okay. So this is the strain solver obtained. If we don't consider, if we don't calculate a strain, this is the fully strained condition. That's the strain is decided by the composition to the surface. So this is not calculated. It's just assumption that you simply say, okay, the strain is Indian, how much Indian atom to the buffer, and you calculate the local strain. But this is a comparison that if you consider about the strain calculation, you can find that ideally this part, this high Indian, you should have larger strain, but it will relax slightly in the lateral direction. But like the strain change in here is larger, but if you actually solve the space, you can find that some more compressive here, but a little bit strain relax in the lateral direction. So we still need to consider about the strain in the quantum world because the simulation results suggest that there is something different.
Right.
Yes?
You're saying on the left that's the unrelaxed, right? Even done in mechanics, that's
Totally unrelaxed.
That's the local relaxation from the local comp.
Yeah.
Right. Okay.
Yeah.
So that's the converged final strain with the coherent layer.
Yeah, this is the final strain.
Yeah.
Yes.
Still coherent.
Still coherent, yeah. Yeah, I mean the lattice is still bounded, not.
You have EXX and EY both on the left, and you separate them.
Epsilons.
Has both EXX and EY. So two matrix elements.
Oh, this is strain in the x direction.
Right, I know, but the leftmost box.
Oh yeah, because this is just assume the composition, so lateral strain is the same.
Oh, they're equal.
It's not calculated. It's just how many composition, then refer to the buffer. So it's not calculating result. It's just a very simple assumption. Okay. So after you calculate strain, you can calculate the piezo field. And with the strain value, you can calculate the piezo field. And if you take gradient of piezo field, you get a polarization charge. So polarization charge only will induce when you have a polarization difference. Okay, so that's a difference. So if you purely have a same material, you won't get any polarization. But if you have a heterojunction interface or composition fluctuation, you will get the fluctuation potential. Okay, then let's go to the numerical detail. You want to solve the Poisson equation. So the ideal Poisson equation that you solve is that you either consider potential V of psi, somebody use psi, and it's equal to the total charge, and you have polarization charge, and you have other charge like trap charge, everything you can put on the right-hand side. But the problem is that if you want to solve Poisson equation, actually carrier density is the Fermi integral of n, density of state, this one, and it's like a Fermi half integral of this 10. Then, of course, if you think that it's a Boltzmann approximation, you take off 1, then you can say it's NC exponential EFn minus EC over KBT. So this is a Boltzmann approximation. But in reality, you have a factor. You have factor that because you do the Fermi-Dirac integral to this one, you have a factor. Okay. I mean, numerically, if you want to consider about the Fermi-Dirac integral, you need to consider this F. So also the same for the holes. So you have NVF and this term. Okay, so just like what the equation is that, okay, if you consider about Fermi-Dirac integral, the Drake diffusion term is not just mu n e partial EFN partial. You need to consider this factor. So that makes the simulation very complicated because you cannot simply use exponential form. You need to put this factor, and this is I must say, there's no analytical solution. So it's a function. It's an integral function put in the code that you need to generate the integral. Okay. Then the second is that this equation actually is divergence square E. If you use the Boltzmann approximation, you still can observe this is a nonlinear equation. So it's a divergence square EC exponential minus EC. So it's just like AS equal to exponential S. If you want to solve this problem, you will never solve it analytically. So you need to, if you want to solve by numerically, we need to change this nonlinear term into a linear term. So we take the Taylor expansion of the EC, and we get delta EC, and we assume that EC is a good guess. Okay, and if EC is a good guess, then delta EC should be small. So delta EC, exponential delta EC can be taken with a Taylor expansion, and we can change this equation from, originally we want to solve EC, but now we don't solve EC, we solve delta EC. Okay, and the delta EC, if your EC0 is a good assumption, then this equation change from nonlinear equation to a linear equation. But you need to solve iteratively. So that's a difficulty for solving Poisson equation. So you can find that not many students can finish this part. So you will make a lot of mistake in this code. The second thing is the carrier density. So we use, the second step is that we solve the landscape equation. And the landscape equation is that we get, from Poisson we get the EC. Then we solve landscape, we get 1 over UE and 1 over UH. So the problem is that in the real device, when you operate, the potential minima is changing in different BIOS. So if a higher potential barrier, you have some inaccuracy. So if your reference potential is too high, we need to shift the reference, okay, to just Marcel said that shift to the potential minima. But after we solve it, we need to shift it back because we want to go back to 3 diffusion. So you cannot keep the potential shift up in the simulation. So we need to shift it back. Okay, so that's the second key point. So carrier density is calculated by LDLAs. Okay, so we need to respond to his question is that we need to keep this carrier density in the, because even we say some carrier density is localized, not movable, but this carrier density will fit back to the Poisson equation. And the Poisson equation need to consider this charge. Otherwise, the bending of the Poisson equation would be wrong. So we still need to keep this term, the total carrier density in the simulation, okay. Then the final part is drift diffusion. Drift diffusion is even difficult to solve because this is mu n divergent EFN. So if you choose n as a variable, like PN diode, if you can imagine that in the PN diode, in the P side, in the PN diode P to N, then the carrier density in the depletion region change in orders, even for a small space. So using the finite difference of finite element to solve in the discrete domain, you change in small deltas, your carrier density changes by 1 order. So it's impossible to directly solve the drift diffusion. You cannot directly use the finite difference to take a description of n. So you need to take treatment is that either your n carrier density is function of exponential EFN, so n need to be is exponential form plus the modified term f of f1 over half. So you need to consider this, and you need to expand this equation into a nonlinear form again, and you solve the delta n or delta EFN. Okay, so that's the difficulties in this part. And if you don't want to do this, some people will suggest use Shafter-Gamma approximation. They tell you that the carrier density distribution is an exponential decay. So if you want to find the middle point of carrier density, you cannot simply use linear interpolation. You need to consider about the exponential decay. That's the key point. Okay, so you can use this way or use Fermi level as a variable. But even you use Fermi level, it's not take gradient of this because inside the n, there is a Fermi level inside. Okay, so the variable is hidden inside here, so you cannot just take divergence of this. You need to take this. So that makes up. Okay, so finally, if you overcome this, we already overcome the drift diffusion part. So you will find that if you already have a Poisson drift diffusion solver, Then the only things you need to change is that when you're counting the carrier density, originally you use EC, now you change N into 1 over UC. So that's why I say, I tell you myself that we actually finish the code in 1 week. And of course, we spend a lot of months to debug. Okay, so it's pretty simple, and this I feel that this method is pretty beautiful and simple, straightforward to do all the rest work. So if you have some already built-in solver, you can simply apply this model to solve it. Okay, so that's the time difference is huge. That okay, in a 3D Poisson, because Poisson problem is a boundary value problem, so you just solve the inverse. So for this node size, with this node size, if you want to solve the Poisson with inverse, then it's 25 seconds. And 3 diffusion, there are 2 equations, so it's double, 50 seconds. And for localization of landscape, it's also another 2 boundary value problem. So the total time is 125 seconds. Okay, but if we want to use the eigen solver to get eigenvalues over 100 steps, then okay, it takes us 1 day, almost 1 day. But just to tell you, the carrier density, we need to solve iteratively. So we need to initial guess EC, and we get a delta EC. So it's iterative. You cannot just 1 step. If you say 1 step, and then that's fine. It's just 1 day. But if I want to get converge, typically at least 5 to 20 steps. And if it's 5, then it's 5 days. If it's 20 steps, then if you want to do the Poisson, it's 20 days. Okay, so it depends on how it converges. If it converges 200 steps, then you know the time, 200 days. Okay, so sometimes it happens quite often. And we want to solve IV, so we have a 45 bias point. So with this Poisson 3 diffusion, we just solve it in 1 day. And we calculate that if we want to use Poisson Schrödinger, it's almost more than 1 year. So it's a significant improvement to the traditional Poisson DD Schrödinger solver. Okay, you can find the difference. It's just a very common server with A code and the memory like 20 gigabytes. So it's affordable in your lab to do this. Okay. So finally, it's a simulation result. Simulation result, I'm interested in the carrier transport. So this is EC, I Claude showed this, and this is 1 over U. So you can find the potential is smoothened in EC over 1 and compared to 1 over U. But because the whole affected mass is quite large, so you didn't see too much difference for the EV and the 1 over UH. Okay, so that's a difference of this. And then this is a current flow, and then you can find that the current, some position that you have a higher current density, and some position you have low current density. So you can observe that carrier flows through certain potential minima in the potential barrier, and then we combine here, and they just flow like a collective wave in the simulation. So if we go to the IV curve, you can find that okay, the IV significantly reduced if we consider the landscape theory, the blue one. But if we just consider the Poisson 3 diffusion, also including the fluctuate potential well, okay, this is the first paper we published is the red line, and the second one for including the landscape model is changed from red to blue. So it's also including the quantum confined effect and a little bit tunneling effect, just like it's including the quantum potential. Okay, so this is the carrier density solved. So if you just solve Poisson 3 diffusion, don't solve the landscape, you can find it's just like a particle model. So the carrier density very, very fast. But if you consider about wave properties, then it's more like a normal wave dispersion in the lateral condition. Okay, so So this is the IV curve in the log scale. So for perfect LED, typically the slope here should be good. Okay. So if you consider about the ideality factor, that if we consider the landscape model, we got the ideal factor in local region that will drop and then increase, and the factor is around 1.5. And this is a trend that observed in a good LED from, I think, Osram or Osram, yeah. Sora, yeah. You can see that there is an ideality factor decrease and then increase. But if we don't consider the quantum effect, then we cannot observe this sharp region in the simulation model. And this is IQE. IQE that this is use the normal quantum wave and fluctuate with 1/u, and the older way we use. So the carrier density is not so high. We consider 1/u, so the droop is in between. That you enhance the OJ enhance the localization enhance the droop effect, but it's not as strong as the old model we did without consider about the quantum effect. So that's a difference. So we get a pretty good fitting. Okay, and how many times I? Okay.
3 more minutes.
Okay, then I show you that on the green. On the green, we have some problem. Because green, you have very, very strong piezoelectric field. So even we consider about the fluctuation, okay, we reduce the turn-on voltage, but still far away from the simulation, not experimental result. Then we found that there's some papers show that in the green, maybe because larger strand, the quantum wave quality is not flat. But some people disagree because they feel that the experimental evidence show that the quantum wave is very flat. But that's fine. So I jumped the Boynton we study. Then we think that if we include the thickness fluctuation, then first we check the emission peak is right in the green. And if we include the thickness fluctuation, we find something interesting is that with different kind of thickness fluctuation, of course, we found the turn-on voltage drop significantly if H is equal to 0.489. Okay, and the IQE doesn't change too much. Actually, even this one has a better IQE. So that means the Indian composition here is lower. Then we try to check what's the influence of the thickness fluctuation range for different LA and LB. And we found that if LB is within 30 nanometer, the turn-on voltage is already similar to the experimental result. So this is around 30 nanometer. And then we check that no matter how the potential fluctuation in LA distance, no matter how we increase the LA, the turn-on is fine, but you just increase slightly in the resistance. So LA can go from 50 to 350, and I guess I cannot going up because of the computation limitation, but I guess that if we go to 400, 500, it probably just increase slightly still keep the same trend. So we think that then the problem is that what's the origin of this thickness fluctuation? Okay, so we guess that this is range about 30 nanometer, and the possibility is first is the dislocation. Because the dislocation density is around 10 to 8 to 10 to 10, just like Suji talked in the morning. So if you think about the dislocation spacing, then typically effective range of the dislocation is around 30 nanometer, because if you consider dislocation center and the affected area. And if the spacing is 10 to 9, then the spacing of dislocation is 350. So if you consider for green, if you have a dislocation density of 10 to 9, it's just like this case. And if you have 10 to 8, the distance is 700 nanometers. And then it's possible that It's the orange. And the second orange is that people try to reduce the turn-on voltage by using VPIT. And the VPIT is something that typically open in a dislocational range. And the density of VPIT is similar order. So it's also possible reason that experimental has a lower voltage. So including the quantum wave thickness, we found that this dash is the experimental result, and the trend, and this is a simulation result. You can find the trend is very close, and we have a smaller turn-on voltage. That's because this is a vertical study, and we don't include the shear resistance. And if we put some shear resistance, we can get more close fitting of the IV curve. But turns out that the IQE curve is not very good trend. The IQE drop, and then the efficiency drop and then increase. But in the simulation, it looks like continue to drop. But some people suggest that if you grow more quantum wave, the reason to grow more quantum wave is not for carrier balance. It's that the quantum wave in the top one quality might be better. So if we put better quality for more quantum wave, we may see a reverse. So ideally, we drop, and then we cannot continue to go back because we put the same non-radiated lifetime. So finally, is the carrier diffusion. So to study the carrier diffusion with a tree diffusion with landscape model, we study a NIN structure. The reason why I study NIN is I want the quantum wave to be fully populated by electron density. So like modulation doping that is populated by electron. Then we put a local excitation of carriers, like a generation term in this 10 nanometer region. And we observe how the carrier diffuse. So this is a diffusion of holes. So this is a difference. If you don't consider the fluctuation, you can find hole diffuse more. And if you consider about a diffusion, a fluctuation, you can find it's more limited. And this result actually is averaged by, in this case, it's 15 case, and we take averaging. So it's a statistical. If you just see one picture, you can see a large vibration. But if you take averaging, it's just like exponential decay. Very beautiful, and you can get a diffusion length is 81 and 179. But electron is even more significant. If we put a PIP, then it's a diffusion of electron. If you don't consider fluctuation, your carrier diffusion length is 6,000, just 6 microns. It's quite long. But if you consider about fluctuation, it's limited to 700 nanometer. So that means what? That means this number maybe explain that why the gallium nitride have a dislocation density 10 to 8. If you have 10 to 8, the diffusion length is like 1 micron. So if you have fluctuation potential, even for electron, your diffusion length is limited by fluctuation potential for limited to 0.7 micrometer. That means your carrier has less possibility to diffuse into the dislocation center, and it might give you some idea why you get very good efficiency in LED. Okay, and if you consider electron and hole simultaneously, you can find hole is like 80, and the electron is like 700. So it depends on which mechanism dominate in the system, and it could be some factor that if you have dislocation 10 to 10, then some electron will be captured, but hole is still localized. So then that provides some hint for better efficiency in LED. Okay, thank you.
Thank you. So just to pick up on the last point you mentioned.
Ignore me. Just ignore me. Ignore me.
Your logic would say that pure gallium nitride quantum wells would behave worse than InGaN because there are no fluctuations that slow down the carriers.
No, I didn't say this. I just say the fluctuation potential limit your diffusion length.
Right, so in gallium nitride...
In gallium nitride, if your quality is good, you don't have problem. But if your quality is bad, you have problem. Do you know my point? I mean, K nitride, if you don't consider fluctuation, your diffusion length is longer. So if you have very high density of dislocation, you have very high possibility to be captured by the defect.
Right, and so my question is that consistent with what's known experimentally? I thought gallium nitride, pure gallium nitride quantum wells had a higher efficiency than InGaN, but maybe I'm wrong about that.
No.
No, but they can be high. They can be high. They can they're low.
It's not. I don't think it's better because in UV, we still have problem for the efficiency. K nitride UV 317. If you put, I think in UV IQ is not good.
Historically, so this was material which is more than 20 years ago, but historically, Suji said that as soon as he put 1% in gallium nitride, these gallium nitride LEDs, he got much more light.
But it's not so simple. Because later, Nichia showed some very bright pure GaN quantum well, very high efficiency. Nichia has results. That's not a fundamental result.
No, sure, but for poor gallium nitride, at that time it showed that diminishing the diffusion length improved the efficiency.
I mean, you have to compare apples with
Be-
apples, of course.
I
I was thinking of similar dislocation densities, okay? And so
But
I'm not sure I hear a clear answer on whether...
I don't
pure
have
gallium
clear
nitride-
answer for you because I'm not sure that, because later on, I mean, the new result with better cross quality, the dislocation is improved. Even you use GaN substrate, so you cannot compare to the older one. So, I mean, there are many factors inside. So as long as that dislocation density is as worse as InGaN, probably InGaN can provide better efficiency.
Any other questions? Gotta go quickly now. Very concrete question. Now you show diffusion length calculator. In diffusion length, you have two components: diffusion coefficient and lifetime. How did you calculate lifetime for this?
Oh, here is a still three diffusion simulation. So we have ABC coefficient. So the combination is determined by the ABC.
What carrier densities then?
Carrier density, we have, there is a carrier density here, but this is integrate carrier density because I want to see the total carrier density in each plane. Okay. It's like 10 to 19.
Okay, two more questions, that's it.
It's more a comment and an advertisement for a young German female professor. You should at the beginning that you should average this binary distribution over a certain region to get better potential. And I fully agree with that, But you said if you use a binary potential, that the strain would be enormously large and it would be not reasonable. Yes, I agree with that as well. But what this Claudia Schnorr looked at is with NEXAFs at the local surroundings of atoms in alloys. And what I took from reading her habilitation thesis is that Wegel's law about the average distance and all is true, but that locally the atoms rearrange each other by adjusting the angles and not the distances. And therefore, this strain, I think one way to look at this is that the strain argument is wrong because there is no strain because it's caught up with angles. And if you average over a certain area, then this angle rearrangement can be taken out, and you can then again use the strain formula of the homogeneous material. So I fully agree that you should do this average, but I think that's another way of this angular redistribution thing.
Yeah.
Just as a comment, and for
Yeah,
Claudia,
I understand.
work about this angular distributions in the locals or in alloys.
You get that out of valence force field models?
Yeah, we can use valence force field model to calculate the local strain, but the dimension is too large. I just honestly
just
say.
that this is my way to say why it's right to do this average.
I do have the code, so I know how fast it is. Yes.
Okay, last question.
At very beginning you said that you specify the strength of fluctuations by setting the scale for the averaging, the composition, random Lloyd composition, and choose two lattice constants for this.
Yes.
The question is this dependent on the composition of Indian gallium nitride? What to do if we go to aluminum gallium nitride? Can we use this scale? And how does it correlate with the study of exciton emission line broadening when the averaging volume was the volume of exciton? Just related to the wave function of the object.
Acetone, that's another problem, but aluminum gallium nitride, we still use 2A. And if you want to consider about acetone, I think that's another issue. But typically, if you want to consider different bands acetone, you need to solve.
No, actually, when people consider the width of the emission line of exciton, they use the averaging volume built up of the exciton bore radius.
Yes.
And this produces reasonable results for the broadening of the line. And this means that actually we should take the averaging volume with respect to the volume of the wave function.
Yes.
And this means that this average volume should depend on the medium composition. If we go to organic materials, we should choose another volume. And what is the criteria for the?
Yeah, but I think if you consider wave length, then you need to consider about the effective mass. It's related to equivalent effective mass. So for aluminum gallium nitride, effective mass is still high for holes, and the electron it's a little bit increased to gallium nitride. So gallium nitride is 0.2, and I remember aluminum nitride is 0.3. So I think it's similar order. So there's a little bit adjustment may be needed, but we didn't test that case. Yes.
Okay. Is there anything else that has to go forward?
Just a comment about when you said the VFF and the relaxing the structure. How big can you go, or what do you think is the very? I mean, we have relaxed systems with over 1 million atoms quite easily.
Sorry,
100,000 of atoms VFF is quite doable. You were saying that the VFF relaxation, there was a comment that with we are using VFF model to relax actually quite big structures with 1 million of atoms.
Yeah. So why cannot? I mean,
Yeah,
I mean, simulation time is long. It's okay to do that.
Yeah.
So
Okay,
what?
maybe I'll catch you afterwards.
Yeah, I mean, if you use various force field model, you put each atom, and if you want to consider the p-ion junction, and calculate the simulation domain is too large. It's not just quantum well. If it's quantum well, it's fine. Yeah, but if you consider 5 quantum well, aluminum gallium nitride layer, everything put together.
I catch you afterwards.
Yeah. Okay.
Okay.
I'd like to know how many million atoms that is.
How many Indian atoms?
How many million atoms do you need for the complete structure?
Okay, you can calculate. If you have
Let us know after you
p-ion, one.
calculate it. We have to go on. We have to continue now.
Okay, you have 5,000 by 30 nanometer is like 5,000 by 100 by 100. So
Can you
it's
do the multiplication? Let us know what you get. Okay. Thank you
okay.
very much.
Sorry. There was